Hi, my name is Nasnianowski. We're going through Monoidal category theory, a unifying concepts in mathematics, physics, and computing. It's a recent book that just came out. Okay, and what we're doing is we're going through section by section. Okay, so let's recap. Chapter 2 is all about categories. We saw a lot of examples of categories. Chapter 3 was structures within categories, and we saw a lot of things that you can say about categories themselves, whether they have products, co-products, whether they have limits, co-limits, equalizers, co-equalizers. Okay, and we also talked about other things like slice categories and related categories and stuff like that. Okay, great. Now comes the real magic of category theory. And the real magic of category theory is about the connections, is unification, unifying. So making connections between different areas. So that's what this is about. Chapter 4, relationships between categories. Okay, not just looking at categories themselves, but the relationships between them. Okay, and so we're going to start off section 4.1, which is about functors. So let me tell you what a functor is. So so in sets, when you have a set, okay, and you have another set, you can have functions between them, okay? And similarly, within categories, you have a category, you have another category, you have a functor in between them. Usually the functors are written in capital letters, okay? Okay, so what are we going to do today? We're going to define what a functor is, then we're going to do examples, and then we're going to see many different types of functors. I'm going to go through a lot of different types of functors, the functors that do this and functors that do that, and for each of them we're going to see a lot of examples. Okay, and so we're going to see lots of different types of functors and literally a ton and many examples of different functors connecting different categories. And some, okay. So that's what it is. Okay, great. Okay, now, let's go through the formal definition, but before I just want to talk to, there are those people who know about graphs and graph homomorphisms. So a functor is like a graph homomorphism, okay? The only thing, in other words, that objects go to objects, vertices go to vertices, and morphisms go to morphisms. The only thing is, a category is like a graph, but it has this extra composition. So we want the functors to preserve those composition. Okay? Another thing a category has is identity morphisms. So we want the functors to preserve the identity morphisms. I'll explain what that means. But again, if you think of a category as a souped up graph, okay, then a functor is a souped up graph homomorphism. Okay, it's an advance. Okay, that's for those who know graphs. If you know group theory, okay, so functors are similar to group homomorphisms in the following sense. What's a group homomorphism? Group homomorphism. It's a function from one group to another group, such that the operations are preserved. Well, guess what? A functor is a mapping from a category to a category, such that the composition operation is preserved, and such that the identity operation is preserved. So you can see it as advanced of those two concepts. So if you know those two concepts, you'll have no problem going on with that. But we're not assuming that, and so let's go into the formal definition. Okay? This video is going to be a little bit faster paced. By now you should be able to work out things on your own and see it in the book, etc., etc. So we're going to do it a little bit faster paced. Okay, so, and we're going to be less write out formal things, we're just going to say formal things. So, given a category A and a category B, a functor is a rule, okay, that assigns to every object here an object here, and every morphism here a morphism here. So it's different than sets. Sets only have objects. Here we're going to have morphisms too, and so we have to do it. Okay, so let's do that. Let's just say it. For A in here, there's going to be, it's going to go to f of A, and for f, little f, which is a morphism in little a, from A to A prime, this is going to go to f of f, okay, which goes from f of a to f of little a prime. Okay, so this morphism goes to this thing. Okay, great. But we have two requirements. Namely, let's say you have two morphisms, a prime, a double prime. And we'll call this f, and we'll call this f prime. Okay, so we're going to have two morphisms. Conclusion, we're going to have composition here. Okay, then what should the functor do with this? And the answer is the functor should do the following. F of little f composed little f prime is equal to f of f prime composed f of f. Okay, so it should preserve the composition. Okay, let's be careful with this. This little composition takes place in category A. This little composition takes place in category B. Okay? Okay, and it's good to write out where this goes to and where this goes to. Main point, if two morphisms are connected here and can be composed, then the two morphisms here can be connected and will be composed, and the composition should be equal to it. Okay, so this goes to where the image of this composed with the image of this. So again, let's just say it in English, composition is respected. Okay, the other thing is, for any object A here, there's a functor, there's an identity morphism here. We call this identity on A. Great, we want this, well, I want, the requirement of a functor is that this identity on little a, which goes from where? Well, A is going to go to f of a. So this should equal to, A is going to go to f of a. So here's your little object A, and it goes to f of a here. Okay, this little object in B has a morphism too. What's this morphism? It's called identity on f of a. Okay, so we want this to be the identity on f of a. So another way of saying this is that the identities are preserved. Okay, so composition goes to composition and identities go to identities. So it's very simple. What's a category? It's a set of objects, a set of morphisms such that there's composition, such as identities, and you want the homomorphisms of categories or the functors on categories to preserve them. I want to show you another way of looking at categories. I'm sorry, at functors. Okay, that's very important to see, and we're going to see variations of this as we go on. So again, you have a category, you have another category, you have a functor, okay? And the way to think of this is, another way of thinking of this is, you have a functor from objects of A to objects of B. So what did I say? A functor is something that takes objects to objects and morphisms to morphisms. So we're going to call this F sub 0, because those are what's called zero cells. The objects are like little dots, zero cells. Okay? As opposed to that, and including in that, there's morphisms of A and morphisms of B. Okay, and you call this F of 1. So you can think of this functor as splitting in two things, but you want to make sure these two functors respect each other. Okay, and I'm going to draw something that we saw already before when we talked about graph homomorphisms. Okay, and so the idea is as follows: given morphism in A, this is your F0, this is morphisms, maybe we should do capital M, in B, okay, and this is objects in A and objects in B, okay, and this is that's F1, This is F0, and this is source of A. And this is source of B. Sorry. Okay, hold on. We have a whole nother one. It goes as follows. Morphisms of A, F1, morphisms of B, target of A, target of B, objects of A, objects of B, F0. Okay, we want these two diagrams to commute. Okay, what are these? These are actually diagrams in collections. Okay, so let's go through this. So main point, you have little f. Here's a typical element in here. It goes from A to B. Okay, what does this say? This should go to F sub of F. Okay, and I'm going to show you where this should go to and which this should come to. Okay, the source of this morphism is little a, and this guy goes by this to F of little a. Okay, that's what he's taking him. Well, guess what? I want that the source of this is F of A. Oops. Okay, so F of F should go from F of A. Okay, now we have the same thing here, and you have little f going from A to B. Oh, I'm sorry, I shouldn't have done B. I should have done A prime. A prime, okay, and this goes around like this, and like this, and like this, and like this, and basically what we get from that is that F of little f goes to, well, we said where it comes from here, but it goes to F of little a prime. In other words, this is A prime, and go like that. Okay. So this is a way of showing that the sources should match up with the sources should match up with the targets. I'm sorry, the morphisms. I'm sorry. Objects go to objects, morphisms go to morphisms. We want the maps to match up with each other. Okay, very nice. Okay, now there's more to what a functor is, but you have to keep these two diagrams together. These two diagrams are very, very similar to what we saw in graph homomorphisms. Okay, we're going to see these diagrams coming up later on. Okay, so we're going to constantly add to these diagrams, and we'll see it much more. Okay, next, for every functor from A to B, okay, there's the following morphisms of Ham sets. Okay, and so we get as follows: Ham of little a of A comma A prime. That's a typical, take two objects here, you're going to have A and A prime, you're going to have a collection of homomorphisms. These could be a set, it could be a class, I don't care, it could be a collection. Okay, and what we're going to get is a morphism Ham of B from F of A to F of A prime. Okay, so this is something that we're going to have to keep in mind. We're going to determine a lot of properties of this f by looking at this. So let's just make sure we understand what this is. Little f from A to A prime goes to f of little f, which goes from F of A to F of A prime. That's from here to here. Okay, great. Okay, and we're going to see lots of things about these. Okay, great. Now we need all the room we want because now we go through a series, lots of examples. Okay, simplest example, identity functor. Okay, so for every category A, there's a functor from A to A called identity of A. Okay, that's an interesting thing. We're seeing common themes here. So within every category, every object has an identity morphism, and now we're saying every category itself has identity morphism. Okay, it does stupid things. So identity on A of little a equals little a. Identity on A of F is equal to F. Doesn't change anything. Okay, but we'll see it's an important functor. Okay, let's do another important functor. Let's look, examples. So let's consider the n, the natural numbers. Think of it as an ordered set. Okay, a partial order, or total order, actually. Okay, and I want to make a functor from n to n, and I want to call it plus 5. Okay, so this is a stupid functor that takes any natural number and adds natural number to it. So let's do it. 32 plus 5, okay, equals, what should you put in? It's equal to 37 over here. Okay, 32 plus 5 is 37. Okay, so you take an input here and you get an output over there. Okay, now I have to show that this is a homomorphism, okay, which means it respects the morphisms here. So this is how it's defined on objects. The main thing is, how is it defined on morphisms? So if you have, what are the morphisms here? Well, there's a morphism from m to n if m is less than n, right? There's a single morphism from there. So let's just do this. So what's it going to come to? Well, if I... m is going to go to m plus 5, n is going to go to n plus 5. There's going to be a morphism from here to here also. Okay, because if m is less than n, then m plus 5 is less than n plus 5. So that takes care of that. Okay, what about identity? The identity of m, okay, m is a typical element in here, plus 5, okay, is going to go to, okay, the identity of m plus 5. So here's a typical element. In here, there's a typical element m. Okay, it has an identity morphism. And here is a typical element m plus 5. It has an identity morphism. This identity goes to that identity. Okay, great. Let's do some more examples. You don't have to erase. We can do more examples. Ready? Okay, there's a functor that we saw already. Okay, it goes from set to set. Okay, boldface, from set to set, and basically P of S is the power set of S. Okay, let's just remember what the power set is. It's a set of all subsets of S. Okay, so that's a set. Main point is it takes a set, and the power set is also a set. Okay, it's a bigger set, but it's a set. Okay, great. How does it work with morphisms? We're going to see two versions of this, by the way, but that's much later on today, but much later on. Okay, it goes as follows. Let's say you have a morphisms of sets. You have a function of sets from S to T. Then you're going to have a power set morphism. It's going to go from the power set of S to the power set of T. Okay. And how does it work? Well, take X, a subset of S, that's an element in here, okay, and the power set of F on this element, so we'll write it like that, on that element. So again, F is a function from S to T. Power sets takes subsets to subsets. So which subset of T will it take? And the answer is, okay, it's going to take f of x. Okay, namely, those things, do I write it here? Okay, so namely, those things, this is the set of x member of T such that no, sorry, let's write it again. Let's write it a different way. It's equal to those little x, f of x's, such that little x is a member of S. Okay, we could draw a pretty picture of this. Here's your S, here's your T, okay, here's your subset of X, capital X, and F takes this to f of x. Okay, what's the image of this thing? So this is called the image power set function, direct image power set function, and we will do this. We will see other versions of this also. So that's your first three examples. Let's go. There's a ton of more examples. Okay, first of all, some words. A functor from a category to a self, okay, is called an endofunctor. It starts and stops at itself, it's called an endofunctor. Okay, let's look at some more examples. Ready? Take any number, real number, there's the floor of the number. What's that? It's the number below it. Okay, it's the whole number below it. Okay, so this is a functor from the partial order, actually the total order of real numbers, okay, to z, the total order of all integers, whole numbers. Okay, that's the floor. There's also the ceiling. Okay, this is usually written like this, by the way. This is usually written like this. Okay, and this also goes from the real numbers to z. This gives you the real number less than or equal to it. This gives you this gives you the whole number less than or equal to this real number. This gives you like that. Okay, main point. So usually we think of these as morphisms of functions, but, usually we think of these as set functions, but you have to keep in mind that they keep the order in mind. In other words, if r is less than r prime, then the floor of r will be less than, if r is less than or equal to r prime, then the floor of r is going to be less than or equal to the floor of r prime. Okay, same thing with the ceiling. Okay, next. Okay, so we're going to see these later on. We're going to give you a better definition of these. Yes, they are functors, but how are they defined? And we're going to see that later on. Okay, next. You ready? Here's a functor. It goes from set to graphs. Graphs is capital G. Our categories start with capital letters. Graphs. Okay, it's called D. And it's the discrete graph. Discrete graph. Okay, it goes as follows. Given a set, let's just do a simple example, A, B, C. Okay, this goes to the following graph. Where the discrete graph is just 3 vertices. No morphisms in between them, no edges, no nothing. Okay, so that's the discrete graph. So given any set, okay, there is a discrete graph that corresponds to it. Just the objects of the set are the vertices. Okay, more important, if there's a function from one set to the other set, then there's going to be a graph homomorphism. Okay, but it's a trivial graph homomorphism because this set is going to go to one of these sets, so you have S to T. S is going to go to the discrete set the discrete graph on S, the objects of S, T is going to go to the discrete graph, and the graph homomorphism is just basically going to take the objects of this graph to the objects of that graph. There are no homomorphisms here, and which object should it take to, will it take to? Answer, whatever the function says it should. So this function from f, little f from S to T, is going to describe this graph homomorphism. Okay, more examples. Okay, by the way, what this is saying is that you can do a lot of set theory within graph theory, okay? But just look at the discrete graphs. Okay, so let's look at the category of groups. Okay, what's a group? It's a set with extra structure, okay? And there's a functor called to the category of sets. Okay, so this is capital groups, capital sets, okay? And this functor is usually denoted with a capital U. Well, U stands for underlying, and this is what's called a forgetful functor. Forgetful functor. Okay, and the idea is as follows. What's a group? It's a set with extra operations. So a typical group is something like this. You have G, you have a multiplication, a sum operation, you have an identity, you have an inverse. Okay, this is a typical group. Okay, and what it goes to is G, just the underlying set. So U stands for the word underlying, okay? The underlying set. Just tell me what the set is, that's what it output. So think of these things as sets with a lot of structure. If you forget the structure, you go here. More importantly, if you have a group homomorphism, from G to G prime, okay? Well, what's a group homomorphism? A group homomorphism is a function from G to G prime such that the operations are preserved. Okay, and I don't have to write it all out. The operations are preserved. Great. Well, this is going to go to a set G prime, so it's going to forget the rest of the structure and just going to go to the set G prime, okay? And guess what? So if you have a graph homomorphism like this, it's going to go to a set homomorphism. What's a graph homomorphism? It's a function from set to set that preserves the operation. In particular, it's a function from set to set, from a set to a set. So you have that. Okay. Okay, so this is under forgetful functors, and we're going to see a lot of forgetful functors in 5 minutes. Okay, so we're going to see a lot more of forgetful functors, but whenever you have something with more structure, you can forget that structure. Okay, great. Let's do some more examples. Like I said, we're going to do tons of examples today. Okay, so let's do this. Be a set. Okay, and now I want to describe two functors. Okay, one is called L of B, L for left, and it depends on B. And it's a stupid functor. It goes from set to set, so it's an endofunctor. Okay, but fine, we'll call it a functor. Okay, and it's defined as follows. Take a set A. It goes to, you ready? A cross B. The Cartesian product of A and B. Okay, that's it. That's it. Okay, take any set A and just do the Cartesian product with A cross B. So you get pairs of elements here. Okay, great. What does it do on morphisms? You always have to do this. Whenever you talk about a functor, you have to say what it works, what it does on objects, and what it does on morphisms. So take another set A prime. Okay, there's a functor here. Well, this A is going to go to A prime cross B. Okay. This functor depends on B. It always just takes the product of that. Well, what will this morphism be? It'll be the morphism F cross, that's both of them are cross, so parallel processing identity on B. Okay, now this is going to take a little time to think about, okay? For example, you have a little element here called little a comma little b. That's an ordered pair here, and it's going to go to f of a, that's a little element in there, comma b. Okay, so this is a nice functor. And you have to check that it preserves composition. For example, if you have another morphism, f and f prime, it goes there. It's going to go to a double prime cross b, and it works here too. F prime cross identity on b, and you're going to get something nice here. This goes here. Okay, so you have to worry about it. You have to worry about identity on A, that it preserves identities. There's a lot of things to do. So this is one functor. It's called left. Now we're going to do another functor, R sub B. Also depends on the set C. So B is a set. And so we have RB. It also goes from set to set. It also goes from set to set. Okay, just like this one. Okay, you have the left and the right. Okay, and RB of, I call this C, instead of calling it A, C is a set. Okay, so this is a set. Where should it go to? And the answer is, it goes to HOM within set. So, set homomorphisms from B to C. Okay, this is a little bit more complicated than this, so we're going to have to go through it a little bit more carefully. Okay, so let's do it. So that's what it does on object C. Let's say there are two objects, well, fine. Let's say RB of C prime is going to equal to HOM of sets, set homomorphisms from B to C prime. Okay, and now let's say within set you have a function f from C to C prime. Well, guess what? You're going to get RB of little f. Now, how should this be defined? It has to go from here to here. Okay, and the answer is as follows. Let's say you have a homomorphism from B to C. We'll call it G because we call this f. Okay, well, guess what it does? Now I want a homomorphism from B to C prime. All I do is look at this homomorphism from B to C, okay, and compose it with this homomorphism. And then I get a more homomorphism from B to C prime. That's in here. So from B to C is here, this is G, this is G composed F is here. Okay, let's just think about what this is. And now it looks strange, but it happens all the time here. Okay, so basically B is your set thing, C is your target, okay? And you're looking at all morphisms from B to C. You sometimes change your target, and you want to look at all your homomorphisms from B to C prime. And if you have a morphism from B to C, and you have such a morphism, then you have a morphism from B to C prime, like that. Okay, there's still more to check. We're not going to do it. It's done in the book, but we're not going to do it. Namely, you have to show that this preserves with composition. In other words, let's say you have C to C double prime. Okay, and you get another one. And you want to make sure that these all compose. And the fact that this is associative, composition is associative, works very well. Also, you have to worry about identity morphisms. Okay, anyways, these two functors, LB and RB, are going to be very, very related to each other. Okay, and it's going to show up in computers, it's going to show up everywhere. It's going to show up in algebra, it's going to show up in set theory, it shows up everywhere and anywhere. We're going to see a lot of it as we go on. Okay, great. We're going to come back to the LB and RB many times. Even within chapter 4, we're going to see it. Okay, one more example, and then we start talking about some properties of things, and then we get into different different types of things. But one more nice example. Okay, you have a functor f. It goes from sets to monoids. Okay, let's just remember what a monoid is. A monoid is a set with a composition and identity and associativity. It's a graph without an inverse, for those of you who know that lingo. Okay, and basically this goes to here. S goes to S star. That's for computer scientists. What this is it's here's sets. These are words that are made out of letters from this set. So for example, if this set is equal to x, y, z, then a typical element here will be x, z, z, x, y. That's an element of the monoid that's made out of. So this is the set of all words of this monoid. Great. Now, this monoid has an operation. What's the operation? Well, composition. Not composing two maps, but concatenation of two words. So if you have another word, z, y, z, x, x, y, z, okay, then you can compose them. Okay, I think I made it. Okay, and this gives you another word made out of x, y, and z. So here's a typical way the function works. Here's your alphabet, okay, and these are words made out of those alphabet, okay. So this is called your free monoid homomorphisms, okay. Okay, great. This monoid, does it have an identity? And yes, it does have an identity, okay. The identity, or the thing that does nothing, is called the empty word. Okay, take a word, concatenate it with the empty word, and you get the same word again. So that's not very interesting. Okay, great. Now, I want to see how this functor acts on morphisms. So let's say you have another alphabet, which you might call A and B. Okay, and you might say X goes to A and Y goes to, X goes to B and Y goes to B and Z goes to A. Okay, make it up. Okay, okay, great. So we're going to call this the set S. We're going to call this S prime, and I just described a function f from S to S prime. Okay, I'd like to know how this goes from this set to this set. I'm sorry, from this monoid to this monoid. And the answer is, you ready? There's going to be another monoid called S prime. And the typical elements in this monoid are words made out of A's and B's. Okay, so let's do some typical things. So here's a typical thing. B, B, A, B. That's a typical element in here. And here's another typical element. A, B, B, A. Okay, that's another typical element. And you can concatenate them here. We'll do it called concatenate prime, just to make a separation. So this is a typical monoid element here. This is a typical monoid element here. And you can concatenate those two words, and you get that. Okay, great. But now, since I have a function from S to S prime, I need a morphism. I need a monoid homomorphism from S star to S prime star. Okay, and it works very nicely. Here's what it does. Here's a typical element in here. It's going to go to f of x, by the way, that's a b, dot f of z, dot f of z, dot f of x, dot f of y. Okay, so let's see what this is. This is f of x is b, f of z is a, f of z is a, f of x is b, f of y is b, Okay, so this word is going to go to this word. Okay, just look at the image of each of its letters. Again, this is the alphabet for S. This is the alphabet for B. If you have a function, that means you're mapping letters from this alphabet to letters of that alphabet. So if you have a word in this alphabet, you can map it onto a word in that alphabet. Okay? And you have a lot of things to check. For example, the identity morphism is the identity on the monoid. Okay? And composition works nicely. A million things to check, but this is very nice. This functor has a lot of names. It's called the free monoid functor, and in computer science it's called the list functor. Okay? You have a list of elements. You have a bunch of elements. You can make lists out of them, and you can concatenate them. So this has a lot of different names, and the important thing is it shows up in a lot of places. It shows up in algebra, and it shows up in computer science, and probably other places too. Okay, great. Okay, great. Now, so we just saw like 5 or 7 different examples of functors. We're going to see a lot more of examples of functors. But now I want to talk about properties of functors, and the idea is as follows. Let's remember about sets. So given a function of between sets, we said pretty much there's 3 things we can say about this. It's one-to-one, which means 2 different objects here go to 2 different places here. It's onto, which means every single object here gets hit by something here. And then we said it's an isomorphism. What's that? Well, if it's one-to-one and onto, it's an isomorphism. What does that mean? It means every object here goes to exactly one object here. Every object here comes from exactly one object here. Okay, well, that's what we talked about when we were talking about sets. We're not talking about sets anymore. Now we're up to talking about functions, functors, between 2 categories. Okay, and so we have a lot of different things we can say about this functor. Okay, so first of all, we have a lot of different potential properties that we can say about this functor. Okay, so first of all, we can talk about objects. Okay, and just like here, we can say the same thing about objects. Okay, how does this map here from this to this? And the answer is, we can say it's injective. Injective is a fancy way of saying one-to-one. Okay, we can say it's injective on objects. Okay, we could say it's surjective on objects. Okay, that means every single object here has another object here that hits it. Okay, say injective on object means 2 different objects here go to 2 different objects here. That's what that means. And then we can say bijective on objects. So a fancy way of saying onto is surjective. And a fancy way of saying isomorphism is bijective. Okay, bijective means both ways. Okay, that's just another way of saying isomorphism. So for every functor, we can say, sometimes we could say some of these. Sometimes they don't have any of these properties, but that's fine. Okay, great. Now, but there's a whole new dimension for functors, because sets just have elements. Okay, functors also deal with objects, which are like elements in the category, but they also deal with morphisms. So there's 3 things we could say about those, okay, for morphisms. And what are the 3 things? Well, remember this. For every functor, we have this type of morphism. Okay. a morphism, the image of a morphism goes in here, and this is the collection of all homomorphisms. Okay, so again, I don't want to use the language of set theory, but you should think of this as a set of morphisms. You should think of this as a set of morphisms. Of course, these categories might not be set based, or they might have more things, or there might be a class or just a collection. It doesn't matter. But there is such a morphism. So given any functor from A to B, you have this. Again, this is A, this is in B. Okay, now we have names. Okay, we say the functor is full, the functor from A to B is full if this homomorphism is onto. What does that mean? Given anything between f of A and f of B in B, it comes from a morphism from here. Okay, so if you have some object f of A and you have some object f of A prime, doesn't necessarily have to come from f of A and f of B, okay? Then if there's a morphism from here to there, it comes from a morphism in here. So that's another way of saying that this function is onto, or surjective. Okay? Another thing we can say is faithful. Again, that's the word that's used, faithful. Okay? And what that means is two morphisms go from here, two different morphisms here go to two different morphisms here. Okay? Another way of saying this is this morphism is 1 to 1. Okay? So let's just draw a picture of this. You have A to A prime. You have, if these two are not equal, then these two are not equal. In other words, if this is f and this is f prime, and this is capital F of f, and this is capital F of f prime, then if these two are not equal, these two are not equal. Okay, if something is not faithful, then two different morphisms can collapse to the same image. And we don't. Okay, so we'll see all types of things. And finally, if it's both full and faithful, just like if it's injective on objects and surjective on objects, it's bijective on objects. This and this implies bijective. Okay, if something is 1 to 1 and onto, then it's also an iso. So too, if something is full and faithful, we call it fully faithful. Okay, so we have three possible things we can say about objects. We have three possible things that we can say about morphisms. Okay, injective, surjective, bijective, full, faithful, and fully faithful. Okay, and whenever we see a functor, we're always going to ask, does this have any properties? Is this in any way special? Okay, one more little thing that I'm going to use, and a lot of people use. Let's say this functor, the objects here are the same as the objects here. Okay, we're going to have this a lot of times. We're going to have the objects in one category are going to be the same in the objects of the other category, but the morphisms might be different. Okay, so in such a case, we don't say, we can say something more than, in such cases, the objects can go to the same objects. Now in that case, if the objects are the same and they go to the same objects, they are bijective on objects. But we're going to use another phrase also. We're going to say it's the identity on objects. Okay, so not only are they bijective, one goes to only one here and one only comes from here. Okay, not only are they bijective, but they come and go from the same element here to the same element here. So we're going to see that concept also. Okay, so this is very nice. Okay, so these are all different properties that we can have about categories. About functors. And we're going to do that. Okay, now we go through different types of functors. Okay, and again, these are just, we're going to see types, examples, 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 types, examples, examples, examples. Okay, so first type of functor is an inclusion functor. Okay, and in general, not in general, usually these inclusion functions, you know what, they're injective on objects, and faithful. They're injective on objects and faithful. They're literally subsets or sub-collections. Okay, so simplest example, finite sets. So this is, the objects are finite sets and the morphisms are functions between such finite sets. We write inclusion functions like this. One includes into the other, so that's you should think of like a subset, and this goes into sets. Okay, so this is all sets, including infinite sets, and we have this inclusion. Sometimes we write it like this, INC. Sometimes we write it like this, INC. Sometimes we just write it without it because we know what's in here and we know what's in here. We don't even have to put a name to it. Okay, let's do another one. Abelian groups. Okay. Okay, I'm sorry. In the book I write it as GPS. But fine, it doesn't matter. Okay, so abelian groups. Let's just remember what abelian groups are. They're groups where the multiplication commute. A times B is equal to B times A. Okay, okay, well, there are special types of groups. So there's an inclusion functor. Okay. Okay, I'm sorry. Functions between two finite sets go to functions between sets. Abelian groups go to groups. Okay, let's do some more. We saw this before, but we didn't see them as functors. We had three different categories. We'll go through, we'll remind you what each one of these categories are. Okay, so this is set, the objects are sets, the morphisms are functions. This is partial functions, the objects are sets, the morphisms are partial functions. Okay, and this is relations, this is the objects are sets and the morphisms are relations between these sets. There are inclusion functors between them. Now, notice all three categories have sets as objects. So all three are inclusions. They're inclusions in terms of the morphisms. A function is a special type of partial function. A partial function is a special type of relation. Okay, but you have to go through that. Okay, but this is the example I wanted to bring in, where not only is it injective on objects, they're actually bijective on objects, because they just all take the morphism. The objects here go to the same objects here, which go to the same objects here, but they're identity on objects. They each take them to the same morphism, the same function. I'm sorry, the same set. So this set S goes to this set S, goes to this set S. A function from S to T will be considered a special type of partial function. That's a total function. And a partial function is a special type of relation. So we saw these three categories. We expressed the fact that they're related, but now we can see them as there's an inclusion function in between them. Okay, let's do some more. Let's talk about numbers, because category 30 talks about everything. Okay, so you have lots of different types of numbers. We want to think of these all as partial orders. Okay, so you have the Q, you have the real numbers, you have complex numbers. Okay, and again, think of them as partial orders. Think of them as partial orders. In fact, these three are total orders. This is also a total order, but that's a little bit more complicated. Okay, and they include into each other. Okay? The objects include into each other. There's only one morphism in between any two objects here, so it's hard to talk about faithful. Anyways, they are faithful, so that's right. So it's an inclusion on objects. Okay? This is a small, relatively small compared to this. These are all countably infinite. This is uncountably infinite. This is uncountably infinite. That's very nice. Okay, great. Guess what else we have? Okay, matrices. Okay, these are matrices with natural number entries. These are matrices with whole number entries. These are matrices with rational number entries. These are matrices with real number matrices. These are complex matrices. Okay, and they all include each other. Okay, now let's just go through. What is this category? The objects are natural numbers, and the morphisms are such matrices. The objects here are natural numbers. The natural numbers tell you how many rows and how many columns you have. The objects here are natural numbers. The objects here are natural numbers. The objects here are natural numbers. Okay, so just like here, not only are the inclusion functors injective on objects, they're bijective on objects. In fact, they're the identity on objects. Okay, so let's go through it. Here, you're going to have a matrix with from M to N. So a typical element here is a matrix from N to N. I'm sorry, typical element is M. Another typical element is N. You're going to have a matrix from M to N. It's going to have only natural number objects. Well, that's going to correspond to any whole number entries, but these guys can also have negatives as their entries. And these guys can have an irrational number as entries. Okay, but all the morphisms are the same. I'm sorry, all the objects are the same, and they're just, all of these are just the objects are natural numbers, and the morphisms are matrices with these types of entries. Okay, so a real matrix with 4 rows and 7 columns can be thought of as a complex matrix with 4 rows and 7 columns. Okay, and that's that inclusion. Okay, let's remember what these are. PO stands for partial orders. Okay. PRE stands for pre-orders. Okay, so the objects here are partial orders, the objects here are pre-orders. So this satisfies an extra requirement, anti-symmetry. Okay, there's an inclusion from here to here, but notice all the morphisms are faithful. Which, I'm sorry, all the morphisms are order-preserving morphisms, and so this is a faithful inclusion. Okay? One more thing, one more example. N manifolds. Let's remember what a manifold is. A manifold is a topological space that's very nice, and locally everything looks like Rn. Okay, N manifolds are n-dimensional manifolds, and they include into all manifolds. Okay, so this is an inclusion function. N manifolds include into manifolds. These are all types of dimensions, any dimension whatsoever. Okay, and the maps are smooth maps, and the maps here are smooth maps. 2 separate smooth maps go to 2 separate smooth maps. Okay, great. Okay, great. Now, I want to talk about a special type of inclusion function. Okay. Okay, sorry, let's write that again. Inclusion function, functor, is injective on objects plus faithful. That means the maps come and go. Faithful is 1 L or 2 L's, I don't know. Faithful. Okay, the maps include into each other. Now I want to talk about a special type of inclusion function called an embedding. Okay, embedding means literally it goes into, so we write it like this, A embeds into B, same notation, but what we mean is that they go into it, so this is injective on objects, just like before. Plus faithful, just like before. But here, an embedding is also full. Okay. So it has not just these two properties, but these three properties. This has two properties, this has three properties. Okay, full. What that means is that not only is all the maps between elements here go to all the maps between elements there, faithfully, but every single map between them is also in there. In other words, there's no new maps in here that weren't seen over there, which means since we know categories are described by their maps relating to each other, an embedding means whatever properties this is an intuition. Whatever properties an object had in here, it's going to have the same properties in here because it's going to be surrounded by the same maps. It's not only faithful, but it's full in that sense. So it's going to be surrounded in the same maps. So let me give you some examples of this. Finite sets into sets is an embedding. Why? This is the simplest example, okay? Because the maps between finite sets and here are all set functions, okay? They're all set functions, okay? And so here they're all sets functions just between these two, between finite sets. Here they're all sets functions between any sets. So you get the same thing. Okay, so finite sets embed into that. Okay, abelian groups embed into groups. Sorry, I left out the capitals, but it doesn't matter. Okay, why? Because the homomorphisms are all group homomorphisms. So nothing to do with that, okay? Partial orders embed into pre-orders. Okay, why? Because the morphisms are in here are all order-preserving morphisms between partial orders. Well, they're all order-preserving morphisms between here. Okay, and the same is, I'm not going to write it out. Oh, I will. Okay, n manifolds and includes into manifolds. Okay, those are also embeddings. Okay, but there are other things that are not. Okay, there are other examples that are not. For example, the natural numbers the natural number matrices, including into Z matrices, that's not an embedding. Why? Because there are more morphisms than there are here. 1 second, maybe I'm wrong. Right. So a typical element here is M, and another typical element here is N. A typical element here is M, and a typical element here is N. Okay? There are a lot more matrices from M to N here than there are here. So it's not full. So this is not an embedding. This is not an embedding. Okay, great. So one type of function, one type of functor is an inclusion functor. Let's do other types of functor. And the second type of functor is forgetful functors. We already saw one type of forgetful functor, namely from monoids to set Okay, monoids to set. What does it do? It forgets the extra structure in the monoids. Well, you know what? We had magmas are what? They're sets with a multiplication. You can forget that multiplication too. Okay, okay. Rings are sets with two operations, an addition and a multiplication, two different operations. With one of them has an inverse. You can forget that and just look at this. Look at the sets. Same thing with groups. Same thing with fields. With every one of these, you can forget the extra structure. Okay, and you come to a category of sets. Okay. So all these are examples of forgetful functors. Okay, what else? Go back and look at, in the section 2.1, look at the definition of a ring. What's a ring? Well, it's a set with one operation and another operation, and this operation has an inverse, this operation has an inverse, and it has an identity, and this operation has an identity. This one, I don't know what I call the identity, minus maybe, okay? This one doesn't have an inverse, etc., etc. Well, guess what? I can forget some of the extra structure. So, for example, I can forget this structure, and I can forget this structure, and I can forget this structure, and I get out a monoid. Okay? So if you forget the inverses and you forget the second unit, you just get a monoid. Okay? So leave out some of the extra operations and you get a monoid. And you could do this over for any different types of things. If one thing is built on the other thing, if one structure is built on the other structure, leave out those extra structure. Look at the underlying things. So you don't always have to go down all the way to set. Set just leaves just the underlying set. You can go, there's an underlying in every ring is basically a monoid. So there's two monoids in here, and so there's two different forgetful functors. You can forget one part of the structure, or you can forget the other part of the structure. Okay, so you can partially forget things. Okay, let's look at some other things. For example, what's a topological space? It's a set of elements with a topology. What's a topology? It's a way of talking about what's near and what's not. Well, guess what? You can forget about the topology, and then you just get a set. So this is the underlying set of a topological space. We have that. Okay, great. What's a manifold? Okay. A manifold is a topological space where every point looks like the real number, looks around every point looks like powers of the real numbers. Well, in particular, it is a topological space. Okay, so you can forget the other structure. You're not interested in the other structure, and so you get that. Okay, what are the morphisms? Let's do this. What are the morphisms in here? And the answer is the morphisms are function maps that are continuous. Only those function maps that are continuous. So forget those. What are the morphisms in here? They are continuous maps that respect that extra, or smooth maps which respect that extra type of thing so that we can do calculus. Well, forget those and just think of them as morphisms of topological spaces. By the way, these two things can compose. These two forgetful functors can compose, and in particular, you can think of any manifold as a set of objects. Okay, so you get that. Okay. Okay, two more examples of forgetful functors. Two more examples, okay, namely complex vector spaces and real vector spaces. Okay, so let's just remember what these are. These are complex vector spaces with a complex scalar multiplications. These are vector spaces with a real scalar multiplication. Well, you can forget, whenever you have a complex vector space, you can take a typical typical complex numbers, 5 plus 3i, and you can multiply it by v. And you get another vector. Well, this is true for all complex numbers, including the number 5. Let's do 5.1. 5.1. And so there's a scalar multiplication with 5.1 that's in here. Well, so let's do that. Forget the fact that this is also, the scalar multiplication is also defined on imaginary numbers. Forget that fact. Just use the way the scalar multiplication is defined here, and you get out this, real vector spaces. Okay, so you can forget it like that. You can forget, you can look at the scalar multiplication and forget the fact that it's also defined on imaginary numbers, and just look at the way it's defined on real numbers, and you can get like that. So that's extra structure. Okay. One last example. Okay, take a category A. Take a slice category. We saw what slice categories is in section 3.2, section 3.3. Okay, so you know what a slice category is. Typical element here is a map from B to A. That's a typical element. Okay, great. There's a forgetful functor from here till A. And it says what? What's a typical element here? A map from B to A. Well, forget the map to A and just put in B. So forget this extra this and just put in B. Just forget this thing. All the maps are like that. Okay, what's a typical morphism from in this category? Well, it's a map. There's a map from B prime to A, and there's a map like that from G, such that this commutes. Okay, we'll call this F prime. Okay, well, guess what? This map from B to A forgets to B prime, and this map from G to B is a map from G to B. Okay, so there's a forgetful functor from a slice category down to its regular category. Think of a slice category as extra, as A with an extra structure. Forget the extra structure, you get that. Okay. Okay, now, so we had inclusion functors and forgetful functors, and I'd like to look at these together, okay, and we'll do this in a second. Okay, so we did inclusion functors, and we did inclusion functors and we did forgetful functors, and I'd like to look at them from a broad perspective. Okay, you could have a category of A structures. Okay, and the way to think of this, and you have a category, a set of A structures, you have a category of set of B structures. And what you could do is you could say the A structures are special types of B structures. In other words, they satisfy more requirements. These guys satisfy more requirements. So let's look at an example. Finite sets and sets. So these are all sets, and these will be sets, but they only have a finite number of elements. So there's an inclusion function from finite sets to sets. Same thing here. You could have an A structure, and there's an inclusion from these guys to these guys. Why? Because these guys satisfy certain requirements that only some of these guys have. So then there's an inclusion of these guys into these guys. Okay, that's the inclusion function. I want to also look, so you also have forgetful functors. Okay, now sometimes we write forgetful functors like that. Okay, but the main thing is like this. What's a forgetful functor? These guys have more structure than these guys. They're not special types of these guys. These guys have this structure, but it has more structure. And what you could do is you can forget these structures. Okay, and that's what forgetful functors are. Okay? Okay, great. Okay, now, in chapter 2, when we talked about all these different algebraic structures, we can describe them, we can write them or their relationship with forgetful functors and inclusion functors. So for example, let's just go through this. What's a field? A field is a set with two operations, and both operations have an inverse. Okay, one of the operations is a little bit less than an inverse because you can't have an inverse of 0. What's a ring? It's a set with two operations and only one of them has an inverse. So this one has an inverse for both of them. This one has an inverse only for one of them. So this one, that extra structure, is that extra inverse. So there's a forgetful functor. Okay, great. Let's go from here to here. What's a ring? A ring has two multiplications. One of them has an inverse. Okay, and you could. Okay, that's the thing. What's a group? A group is a set with one multiplication that has an inverse. So if you forget that second multiplication, if you forget that second operation, then you get a group. So every ring you can forget some of the structure and you get a group. Okay, great. This is an abelian group. An abelian group is a special type of group. Okay, what's that? This is all groups. Some of those groups have commutative operations, and so those are the abelian groups. So that's a subset of that. Okay, let's go through this. What's a group? It's a set with an operation, and the operation has an inverse. Well, if you forget that inverse, you get a monoid. Okay? Okay, now, you also have abelian monoids. What are those? Those are monoids where the multiplication commutes. Now, you have abelian groups and abelian monoids. You can forget, you can forget the inverse here and you get an abelian monoid. Okay, great. What's a semigroup? So let's do this. A monoid is a set with an operation, okay, with an identity. Well, if you forget the identity, you get a semigroup. Okay? Okay. Just have the operation, and the operation is associative. The operation is associative here. A magma is just a set with, we don't assume the associativity, so you have that. Okay? All these commute, and they're very nice. Okay, now, so what we're going to see is a lot of times, by the way, a lot of times you're going to have a structure and you're going to have another structure, and the relationship is going to be more complicated than that. So this might have extra requirements than this, and this might have extra structure too. So it's not so simple. For example, what's the relationship between abelian groups and semigroups? They're not a subset. They're not a subcategory, but it's more complicated. Okay? Very nice. Now, in the Venn diagram at the end of the book, I write these with such a circle, and these relationships I write like this. Okay? So I'm making that distinction between an inclusion and not an inclusion, but a forgetful functor. Okay? Two different things. This is obvious. Everyone writes their Venn diagrams. This was my doing, and I think it's helpful and interesting, but it's a little bit non-standard. Okay, great. Okay, great. So we're going to see a lot of this, especially in Chapter 8, when we talk about describing structures. It's going to be important for us. These two different types of ways of describing one structure within another structure. How do two structures relate to each other? Okay, great. Okay, great. Next, you ready? You have. So we did a lot of examples of functors. We're going to do more examples of functors. But beforehand, let's go through this. You have a functor from A to B. You can also have a functor from B to C. Okay, we'll call this F, we'll call this G. Guess what? You guessed it. Functors compose 2. Okay, and so we have F compose G. That's very nice. And there's a lot of things to show here. So for example, if you have 2 maps from A to A prime to A double prime, okay, F little f prime, well, you want to make sure that the composition of these, given that this you want to make sure that the composition of these goes to compositions over here with this composition function. And it's not hard to see, and the idea is as follows. And it's worked out in detail in the book, but you have to get a feel for it. You ready? It's not hard to see. If this functor preserves composition, and this functor preserves composition, then the composite functor preserves composition. Okay? Next, this composition is associative. Okay, and we can go on and we can talk about that. What does it mean? Okay, so there's 3 different functors and it's associative. Okay, furthermore, every category has an identity functor, and this category has an identity functor. Okay. Okay, and the identities act like a unit. They act the way they're supposed to. So F composed identity, first do F, then do the identity on B, okay, is equal to F. So it acts the way it's supposed to be. Conclusion, and this is where categories get confusing and categories get absolutely beautiful. Conclusion, not only are each of these a category, but the collection of all categories and all functors between them also form a category. And so here's where you get into the loss of dimension, okay? Because you're on one hand, you're in a category, or on the other hand, you're outside of a category looking into a category, and we're gonna have collections of collections of collections, and it's beautiful. And you see all things. Okay, so we're going to put together all categories and functors between them, and we get what's called CAT. Okay, with capital A and capital T here. Okay, you see, okay, this is the collection of all categories and all functors. And in some sense, this is all mathematics, computer science, everything that we could talk about with categories somehow sits within this thing. And this is this collection, this is where this magic happens, where all these different categories are interrelated with each other. Okay, so we have a way of thinking about these things. Now it turns out that this collection is a little bit too, in some sense, it's a little bit too big, but that's not the point. The point is, we don't usually work with that. We usually work with this category. Okay, this is not all functors. Okay, this is the collection of all category. Of all locally small categories. So the objects are locally small categories. Okay, so let me tell you what that is. Categories are locally small if the Ham sets form real sets. Between any 2 objects of the category, they form all sets. Now, set theorists make a difference between class and sets, and all of mathematics feels nicer when at least the Ham sets are dealt with. So most of the things that we're going to deal with are in here, okay? And the morphisms here are all functors. So that's very nice. We're going to see more structure. This has more structure. We're going to talk about 2 cells or things like that, or higher structure than that. But this is a lot of where we're going to spend our time. Okay, that's very nice. So beforehand, so let's just recap and try to say where we are. We've spent a lot of time talking about individual categories, and then we started talking about relationships between categories, and now we're talking about the collection of all categories and having that. Okay? So it takes a little time to orient yourself, and once you get it, it's perfectly clear and understandable. Now, in order to orient yourself, I want to talk about cat, but I want to talk about cat in a way that's somewhat familiar to you. And so I'm going to bring down a lot of times that we thought about categories, the category of categories, okay, the category of small categories, the category of locally small categories. I want to talk about that, but I want to talk about things that we already did. Okay, so what I want to talk about is different examples of categories that we already dealt with. Okay, so let me give you an example. Okay. So these are all examples in which we're going to use the category of sets. So let me erase that. One of the things we talked about way back in chapter 2 is a discrete category. Okay, let me tell you what a discrete category is. A category with just objects and identity morphisms, because that's the definition of a category. It has to have identity morphisms, but it doesn't necessarily have morphisms, non-identity morphisms between the objects. Okay, so we talked about that, but we didn't think of it as a functor then. Okay, but there's a functor that takes a set and gives out a discrete category. Okay, and so for example, the set could be, what did I do 5 minutes ago? A, B, C. Okay, and then we get the category A, B, C. Okay, but it's a discrete category, so it has identity maps also. Okay, now you should see deja vu now. Maybe I did X, Y, Z, don't remember. You should see deja vu, because you say, oh, I just saw this 2 minutes ago when we were talking about the discrete graph. Okay, so the discrete graph was a functor from set to graph. Now I'm dealing with a functor from set to categories. We're going up to categories. Okay, now, is this really a functor? And the answer is yes, because if you have a morphism of sets, if you have a function, okay, and where this is x, y, maybe I went the other way, okay, something like that, ... okay, well, then you're going to have from this category to this category, okay, there's a discrete category with x and y. Okay, again, only identity morphisms, no morphisms, and this function can map on like that. Okay, so functions from sets go to functors of discrete categories. Okay, again, we saw this the first 10 minutes of section 2.1 when we were doing examples of categories, but now we're seeing it as a functor. It takes a set and outputs a discrete category. We're going to have 1, 2, 3, 4, 5, 6, 7 of these things, okay, where cat, we were talking about categories, but now we're talking about a functor into the categories. So that's very nice. Okay, let's do another one, okay? One of the things I said was, take a monoid. You could think of a monoid as a category, okay, as a one-object category. Well, this contains all one-object categories too. Let's just remember how it goes. M goes to the category that, with one object, and for every guy in here, little m prime, there is a morphism, and the morphisms come and go from the only place that they can go because it's only one object, and the composition, let's do it, the composition of morphisms, M composed M prime, okay, is equal to the operation of the monoid. And besides that, there's also an identity here, okay, and the identity corresponds to the E of the monoid. Okay, so basically we have a functor which takes a monoid and outputs a category, a one-object category. But this is a full functor, which means that if there's a map, a monoid homomorphism from M to M prime, guess what? Then there is a functor from this one object category to this one object category that works, okay? And again, there's a lot of things to check over, namely composition works and the identity. Monoid homomorphisms goes to the identity one object category, things like that. Okay, more. Okay, one of the things we saw, and again in section 2.1, was every partial order. Okay, so what's a partial order? It's a set with a less than or equal to, okay, some operation that satisfies reflexivity and transitivity, okay, or maybe including anti-symmetry, whatever, we're going to say whatever. Well, every partial order, you can make a category out of it. Okay, and what's the category? The objects are the objects of the underlying set, and the morphisms are, well, if this is less than this, then there's an arrow in between them. There's only one arrow in between them. Okay, great. And what is the morphisms in this category? They're order-preserving morph functions. Well, they're going to go to functors, which are order-preserving. Okay, great. Whatever I say about partial orders, I also say about pre-orders. Okay, so there's a functor like this. There's a functor like this. Okay, great. Let's go a little bit quicker here. There's also from the category of groups to the category of cat. Take a group, think of it as a one-object category where all the morphisms are invertible, are isomorphisms. If you want to remember the word, a one-object groupoid. Okay, so we get that. Okay, and so we might call that, we might give this a name. So in the book I call it C. That's a functor that takes a group to the one-object category. Okay, and group homomorphisms go to nice functors, etc. Okay, next. Okay. Okay, let's do another one. You ready? Power set. What's the power set? Okay, the power set takes a set and puts out a set functor takes a set and puts out a partial order. But partial orders are also, we just saw partial orders can go, so it puts out a partial order. Okay. Okay, and the partial orders are special types of categories. So you can think of a power set as a category. You can think of the power set as a category. Just compose these two functors. Okay? Okay, and it's for a morphism here from S to T, it's going to go to, I don't know, the power set of S, that's a partial order, which is a special type of category, to the power set of T, okay, and it goes like that. And we showed how to do this with that cute little Venn diagram. Okay, here's X, this is f of X. Okay, so this is the power set of F. Okay, and it has to, you have to show it preserves inclusions. For example, if X prime is a subset of X, then F of X prime is going to be a subset of F of X. So that's shows inclusion works. Okay, one more example of something we saw already, but we're going to, but we didn't see it as dealing with categories, but as the category categories, but we're going to do it again. Okay, so remember this, you take a category and you take the opposite of it. What the hell's that? Well, the objects are the same and you turn all the morphisms around. Okay, now the way to think of this is that there's a functor, which we can write as this, which takes a category and does gives you out a category. So it's a functor from the category to categories. It's a functor that takes a category and gives you another category, which all the objects are inverted. Okay, so that's the opposite category. Okay, by the way, so let's not write that over here. Let's write it over here. Well, this is actually an exercise in the book, but we can do it now. Let's say you did this twice. Okay, so let's go through this. You take a category, keep the same objects, just flip the arrows. Keep the same objects, just flip the arrows again. What do you get? You get the identity on cat. You get the same exact category. Again, take a category, flip the arrows again, you get the same category. Okay, that's nice. Okay, we'll explain what this means in 3 minutes because we need a new concept. Very nice. So, cat, the category of all categories, is a real thing. We've been using it all along, okay? But now we formalized it and we have an exact definition and we're going forwards. Okay? Okay, great. Let's talk about isomorphisms. So let's remember what an isomorphism of set is. Okay, we saw this picture before, but let's do it again. Okay, an isomorphism of set is a function f from s to t and a function g from t to s such that identity on s, identity on t, if you compose this, you get f compose g, you have f compose g. This is of sets. You can compose these two, g composed f, so you have g composed f. And what does it mean for these two sets to be isomorphic? What does it mean for f to be an isomorphism? That there is this function, and such that this is equal and this is equal. Okay? And it's very nice, but sets are not very interesting topics. The point is as follows. You have just the objects, and basically what it's doing is, what does it mean to be an isomorphism of sets? What it's doing is, it's taking every one of these guys and giving it the name that's in here. And every one of these guys and giving it the name that's in here. That's what G does. Okay? So you're basically, isomorphisms of sets are just renaming. Perfect renamings. So everything in S gets a name by T, everything in T gets a name by S. It's very nice. Okay? But not very interesting. Okay, great. Now I want to talk about isomorphisms of categories. Okay, by the way, when these two things happen, when there is such a thing, we say S and T are isomorphic. Great. Now I want to talk about categories. You have a category A, you have a category B. Okay, what does it mean, isomorphism? Well, now that we know what composition of functors are, we can do the same thing we did here. Namely, there's an identity on A, boldface. There's an identity on B, boldface B. There's a composition of F composed G. There's a composition called G composed F. Okay, and what do you want? Exactly what you think you want. You want this to be equal to this, and this to be equal to this. Okay? So now we have the concept of a an isomorphism of categories. Okay, so what does it mean that F is a functor that's an isomorphism of categories? That means whatever there is for F, doing for F, you can undo it with G. There exists a way of undoing it. Okay, and what does it mean with these compositions? It means that if you do F and then you undo it with G, you get back the original A. If you do G and then you undo it with F, you get back the original B, and you have that very nicely. Okay, so that's an isomorphism of categories, and when two categories are isomorphic, we write them, when two categories have an isomorphism in between them, we say they are isomorphic, and we write it like this, A, 1, 1, B. That's what it means to be isomorphic. Okay, but let's talk in terms of renaming. It's going to turn out that isomorphisms of categories are also not very interesting. And the reason is you're just renaming things. And so it's changing the name, but it's not really an interesting structure. You're changing the name. You're changing the names of these guys into the names of these guys, etc. Okay, it's more interesting than sets, at least, because sets only have, you're changing the names of the elements. Here, you're not only changing the names of the elements, you're also changing the names of the morphisms in between them. Okay, so the isomorphism goes on the morphism in between them. We're going to fix this. We're going to change this. We're going to modify this definition twice in this chapter alone. We're going to modify it a few more times later on in the rest of the book. But keep this picture in mind. It's a very important picture. Great. Let's see some examples of isomorphism. I told you it's not very interesting, but still have to see some examples of it. Okay, so let's go through it. Ready? Examples of isomorphisms. Okay, so let's just go through it. A functor can be isomorphic. A functor can be an isomorphism, and if it has a G, an inverse, okay? And the two categories that are relating are isomorphic. So you got to know the English. English is hard, is also hard. Okay, so some examples. Identity. Identity functors are isomorphic functors. Why? Because they take things, their inverses, compose identities and you get identities, and they don't change. In fact, they don't change the names of things. They keep the names the same. Okay, great. One of the things that we saw at the end of chapter 2 is if you take any category and you multiply it, do the Cartesian product with 1. What's that? That's a one-object category. That's isomorphic to A. That's like not doing anything to it. Okay? So what are these? The objects are ordered pairs where one of the objects are here and one of the objects are here. Well, there's only one object here, so it's like this. Okay, so this is a renaming of this. And a morphism here is basically F, comma, identity and star. That's a typical morphism here, and that's going to go to A prime, F. So it's just a renaming, not very interesting. Okay, let's do two interesting things. Rel op. Okay, let's go through this. What's rel op? The objects are sets, just like in rel. And the morphisms from S to T, let's do this. The morphism from S to T, the objects here are also sets, and the morphisms from S to T is a relation from S to T. We wrote it like that. Okay, well, guess what this is? The objects are sets, and the morphisms are relations from T to S. Okay, but one of the things we saw was that you can take any morphism from S to T, and so you might have a little guy here, S is related to little guy T. Well, you can rename them as T comma S. Okay, so it turns out that these two categories are isomorphic. Category isomorphic to itself. Okay, let's do another one. Okay, let's remember what this is. K is some field. K matrices, the objects are the natural numbers. Don't touch those. Okay, and the morphisms from M to N are M by N matrices. Very nice. Okay. What's this? The objects, I'm sorry, K is a field. The objects are the natural numbers, just like before, and op doesn't affect that. Op doesn't affect that. It doesn't change the natural numbers. But the morphisms from here to here are, from M to N, will be an N by M matrix. Okay? Main point is, if you have a matrix, an M by N matrix A, okay, you take the transpose of that, that's old matrix transpose, you get out an N by M matrix. Okay, and this is nothing. This is no changing. You're just changing the rows and the columns. That's it. You're not losing any information. You're just renaming things. Okay, so it turns out that these two categories are really isomorphic. Okay, by the way, this is interesting. This is self-isomorphisms, so that's pretty interesting. Okay, it's not really self there. You're doing the opposite. We'll see more of this at the end of chapter 6. Okay, so this is very nice. Okay, great. Okay, so that's isomorphisms of categories. And like I said, it's not very interesting because you're just renaming things, and there's not a lot of examples, non-trivial examples. There's a lot of examples, but they're not non-trivial. Okay, we're going to see that when we weaken the notion of isomorphism, we can talk about more interesting phenomenon. And so it gets much more interesting. Okay. Okay, I want to talk about another functor, something we already saw, but it's an example of something we already saw, but I want to bring it up now because we're going to make a variation of it. So take a category A, okay, and take an object in A, okay, and I want to talk about this functor, okay, Ham. Looks like somebody winking. Okay, ready? Ham sets from this guy into, take another guy from that category, and it goes into sets. So let's say A is locally small, so the Ham sets are actually sets, but I don't even have to do that because I'm not being strict about that. Okay, so this guy is going to take a morphism and going to put it in there, and the output goes to set. Okay, if it's locally small, it goes to set. Otherwise, it goes to class. I'm not interested in that. But the main point is, given another guy in here called A prime, so then you get, so A prime goes to Ham sub A of A comma A prime. This is the set of all morphisms in this category from A to A prime. Okay? Such a functor is called a representable functor. Okay? Okay? And so what it means really is it's a functor from A to set, but it's kind of represented by A. The information that describes this functor uses A in a fundamental way. So it represents it. Okay, great. We're going to see this. Oh, I'm sorry. We did this, by the way. We did this before. We called this right of B. Okay, remember this? We had left and right. B is a set. So we did this in the category of sets about an hour ago, but we're doing it again, and we're being very formal about it. Okay, great. Okay, so this is called representable functors, and you have to worry about this. Let's say you have an A double prime, Okay, and so it's going to go to ham A comma A double prime. Okay, and if you have a morphism from A prime to A double prime, there's going to be a morphism going like this. Oh, let's write it out. It's going to be ham A comma F. And basically what it does is it takes a map from A to A prime. Takes a map from A to A prime and composes it with something from A prime to A double prime, and guess what you get? A map from A to double prime. A to A double prime. So it works. But we saw this before. Great. Next. Turns out that functors come in two flavors, vanilla and chocolate. No, not really vanilla and chocolate. They come in two flavors. One we've been talking about all along. They're called covariant. And one we just have to bring up now, it's called contravariant. Okay, so let me explain to you what a covariant functor is. Let me explain to you what a contravariant functor is so you can get it. Well, you know what a covariant functor is. The main point is as follows, that a map from A to A prime with a covariant functor goes to, you know what, let's do it like this. A map from A to A prime, okay, with a covariant functor, F goes to from F of A to F of A prime. Okay, we'll call that F of little f. Great. In contravariant, it's much more interesting. So you have it's not much more interesting, it's the same thing, but slightly different. Okay? Okay, so this is F. Now, a contravariant functor is going to take it, ready, the opposite way. So it's going to go from F of A prime, it's going to go this way. It's going to go contra, against the variance. So this goes from A to A prime, this goes from A prime to A. Okay? You immediately say, hell, I need an example of that. That's different. All the examples we saw are always going following the arrows, but now we have something different. Okay, but before I give you an example, let's just finish off what I'm talking about. If you have another map, F prime, which goes from A single prime to F double prime, okay, guess what's going to happen? You ready? So I'm going to call this F of little f. And this is going to go to F of double prime. Okay, and this map is going to go here. We're going to call this F of F prime. That's this. Okay, and so conclusion, we have the following. F of F composed F prime, that's these guys, is equal to, you ready? Shoot, let's be careful. First, we're going to do this, so that's F prime, F. Notice the order switches. This is F followed by F prime. This is F prime followed by F. Okay, so that's a requirement for a contravariant functor. That's a requirement for a contravariant. It also has the requirement about the identity. Okay, let's just remember the requirement about the identity. That doesn't change. ID of A is equal to ID of F of A. Okay, so these are two sides, two different types of functors that show up a lot. Let me give you an example of a contravariant functor. I'll give you a few examples of contravariant, but I want to give you similar to this. Okay, so remember, this is a covariant functor. F goes from A prime to A double prime, goes like that. Okay, and so we have covariant. Let's change it. Now let's look at contravariant. Okay, so let's look at another example. You have a category A, you have an object A in the category, and then you can do the following. Ham, where A is in the target. Okay. Okay, let's see what this is. you're going to ask for an input here, and so this takes as inputs A and outputs set. Okay, great. Now, here's the more interesting part. Let's see how this works. Let's say you have a map from A prime, let's first do what A prime, how this works on objects. And this takes an object A prime, and it goes to ham sub A of A prime comma A. Okay, and again, this is contrasted to that. This is the set of homomorphism from A to A prime, from A prime to A. Very nice. Great. Let's say we have a homomorphism F from A prime to A double prime. And guess what? This is going to go to ham of A double prime till A. That's what it does. A double prime to A. Okay, great. Now, this morphism, how does it work? Okay, so now we have to be careful. Ready? Let's follow it. You're going to have a map. We'll call it G. And G is going to go from A double prime to A. Okay, that's over here. Okay, and now you have another map, and the other map goes from A prime to A double prime. So it's going to be like that. Okay. Now you compose these, you do F followed by G, and guess what you get? You get a map from A prime to A. So you get a map from A prime to A. That's exactly what you do. So if you start off with a map here, and you pre-compose with this, boom, you get that. Notice this arrow goes down, this arrow goes down, this arrow goes down, this arrow goes up. Okay, contravariant. Okay, we'll call this ham of, notice here. Okay, we'll call it ham of F, okay, F, comma, little a. This we called A comma F, this is called F comma A. It's nice to see these two things at the same place. Okay, guess what? This is also called a representable functor. We represent A, A kind of represents it. It gives it a lot of information of what you're doing. Okay, and we're going to see this a lot in many chapters in the future. I'm going to see actually more of this than this. Okay, but that's fine. Okay, main point, contravariant. Goes the other way. Okay, great. Okay, let's see some other examples of contravariant functors. Let's see some other examples of contravariant functors. Okay. You know, there's a lot of ways of looking at this, but I don't want to do it. Yes, this is also goes to cat, but I want to do it in a set. Now you might say, oh, we've seen this before. Right. We saw one version of this. I want to show you another version of this. Okay? That's contravariant. Okay? And the idea is as follows. You ready? Take a set S, it's going to go to the power set of S. What's the power set of S? It's the set of all subsets of S. Very nice. We saw this before. Now take a map from S to T. Okay, well, guess what? This is going to go to the power set of T. Very nice. And what we saw before is a map from here to here, which basically takes a subset of S and maps it into what is F going to take it to. So I'm going to draw this, but I'm going to erase this in a second, so don't draw this if you were taking notes. This is the power set of F. It takes a subset of this guy and maps it into what F does. And we call that the direct image. Very nice, but I don't want to do that. I want to do it contravariantly. Okay, so this is a contravariant power set function. Okay, let me show you how it works. Okay, it's not so hard at all. Let's first do the Venn diagram. So here's your S, and here's your T, and here's a subset of T called X. Okay, and basically what I want over here is, tell me what is the subset of elements in S that map onto here. Sorry, so this is F like that. Okay, and we call that, you ready? F minus 1 of X. So that's the subset of elements in S that map onto it. Okay, we saw that. Okay, anyways, so names. We're gonna need a lot of names. So this is sometimes called a pre-image functor. Okay, you come back, pre-image functor. Okay, or it's called the inverse image functor. Okay, and it shows up as often as the direct image functor shows up. So we're going to see a lot of that. Okay. Okay. By the way, you can describe this another way also, something that we saw with pullbacks. Let's see if we can do it. You ready? S goes to T. This is F. Okay. And now you have X, a subset of T. Okay. And you take the pullback of that in the category of sets, and you get F minus 1 of X, which is a subset of S. Pullbacks take inclusions into inclusions. Okay, so that takes care of that. Okay, great. So that's a nice thing. Of course, we left out things. You have to show that it's preserves composition. You have to show it's the identity, et cetera, et cetera. This is all examples of contravariants. Okay, great. One more example. No, we're not. Okay, one more. No, we're not going to do another example, but I just want to show you something else. Namely, this whole contravariance, you don't have to use the word contravariance. Okay, so I told you functors come in two flavors, vanilla and chocolate, covariant and contravariant, but you don't need to use the word contravariant. Let me explain to you why. Okay, so you have a functor from A to B. Okay, and I say this is contravariant. Well, this thing is equivalent to a covariant functor. We'll call it F prime, which is related to F. Okay, but instead of going from A to B, it goes from A opposite to B. Okay, so A opposite, what's A opposite? Flip the arrows around. Okay, so what this does is, so if you have a map here from A to A prime, okay, then the contravariant is going to go from F of A prime to F of A. Okay, it's going to go like that. That's contravariant. But what this is if you have a map from A to A, let's do this. If you have a map from A to A prime, okay, then in A opposite, it's going to be from A prime to A. And then covariant from that is going to be from F of A prime to F of A. Okay, and so it's going to be like that. So whenever you have a contravariant functor like this, you can also write it as a covariant functor like that. So for example, that representable functor that we just saw, okay, let's do both examples. The representable functor, we can write it as follows. So let's just remember, here I had dash comma A. Okay, and I said this goes from A to set. Okay, and I said this is contravariant. Okay, but I could also say this is a covariant functor from A opposite to set. Okay, and similarly, the power set functor, I told you is a contravariant functor from set to set. But I can also say it's a covariant functor from set opposite to set. Okay, so we don't need the language of contravariance. We'll use it a lot, okay, but we don't need it. Okay, and a lot of times we're just going to write the opposite, and you'll know what I mean by then. Okay, great. Okay, last page of notes. Okay, not only can we talk about functors, we can also talk about other types of things called bifunctors. Okay, and what do I mean by a bifunctor? It's a functor that goes from pairs of categories to another category. Okay, so that's a bifunctor. Its input is two things. Okay, let me give you an example of a bifunctor. Ready? Ham take a category A, ham, like this. Now, it takes an input here, and it takes an input here, and it outputs a set, assuming A is locally small or something like this. Okay, hold on. It's covariant on this thing, it's covariant on this thing, but if I plug it in here, it's contravariant. So let's write it like this. That's a bifunctor. Okay. Okay. There's requirements for this, and you have to look it up on what does it mean that it satisfies these things. And so you have two maps here from A to A prime and from B to B prime, and you have to go, you have an F here and you have a G here, etc., etc., and you have to worry about it. The book does it very nicely, does it with all the details, but you have to go through it once in your life and do it. Okay? Okay. You also have something called a multifunctor. Multifunctor. Okay, which goes from, so it's a functor that takes many inputs. Okay, and some of them might be opposites, and some of them might not. Okay. I don't know. You can go to many categories also. So those are multifunctors, and lots of requirements for that, and we're going to do that a lot. Okay, let me show you another type of functor that we kind of talked about, but we didn't call it a functor because we didn't have that language. So let's do this. You ready? You have a category. You have this, a congruence. So this is a category. You have this, a congruence. Okay, what's a congruence? It's an equivalence class. It's an equivalence relations on morphisms that respects the composition. That's what a congruence is. Okay. Well, then we can make a category like this. Okay. And what's that? The objects are the same as A. The objects are the same as A, and the morphisms are equivalence classes of morphisms between the objects. We did this in related categories in section 2.3, I think. Very nice. We did this already. Okay, but now there's a functor. From this category, from the original category to the congruence, okay? And we saw this in terms of sets when we dealt with only equivalence relations. We had what's called a quotient functor, a quotient function. Now we have a quotient functor. So this is a quotient functor. Okay, let's just remember what it does. The objects goes to the same objects because these are identity on objects. The morphism here goes to the equivalence class of morphisms that it contains. Okay? So this is called a quotient functor. We had this congruence before, just like, okay, and it's nice. Okay, great. Okay. Okay, the rest of this class, the rest of this video is just going to be examples from all over, and we like them a lot. Okay? And again, what's the whole purpose here? The whole purpose is to show that different things are related by functors. Different contexts, different categories are related by functors. Seemingly unrelated, and yet we'll show they are related. Okay, so let's start with something. Let's remember what this is. This is the category rel. The objects are sets, and the morphisms are relations between sets. Now I want to talk about something else called nat rel. Okay, here's here's a subcategory of this. So this is going to be a subcategory of this. Let me tell you what the objects are. The objects are sets of natural numbers. So 1, 2, 3 of the same form. ... of n. That's a typical object here. Okay? And you could have another object, 1, 2, 3, ... m. Okay? Okay? So this has all, the objects are all sets. Objects equals all sets. Okay? And the morphisms are all relations. Okay. Nat rel stands for natural numbers. Think of these as natural numbers. The objects are just sets of natural numbers. Okay. And the morphisms are all relations between this set and this set. Okay. So it's an inclusion on objects, and it's, I think it's full and faithful on morphisms. So it's an embedding. Very nice. It's full and faithful. Okay, great. Now, I want to do the following. I want to relate, what do functors do? They make relations. So I want to relate relations to matrices. Okay, two seemingly unrelated things, but I want to talk about relations and matrices. Okay, and the way we do this is as follows. F is a functor from nat relations, this guy, to Boolean matrices. Okay, let's remember what Boolean matrices are. The objects are natural numbers. They're going to tell you how many columns, how many rows, and the entries are 0 or 1. Okay, and what I'm going to do is I'm going to relate relations to Boolean matrices. And the idea is as follows. The objects here are sets of natural numbers. So let's do this. So the set from 1 to m is going to go to the number m, stop. Okay? So this is an object in this set. It's a set of natural numbers, the first m natural numbers, and this is going to go to m. Okay, in the book I have different notations to be exact, but we can understand it. Now, let's do another set, 1 to m. Another object here, that's from 1 to n. Okay, and this is going to go to n. Okay, now a typical morphism from here to here is a relation. Okay, so we might call it R. Sorry, I don't want to use the script R. We might call this relation R. Okay, and what R does is it says, you know, this guy is related to this guy, this guy is related to this guy, this guy is related to this guy, this guy can also be related to this guy. It's not a function. This guy can be related to this guy, this guy can be related to this guy, can be related to nothing, etc., etc. That's what it does. Okay. So a relation from here to here is ordered pairs of elements in here and elements in here. Well, we can make a matrix out of that. Okay, and the matrix has the following property. It goes from m to n, so it's an m by n matrix. So if you want, you can think of it like this. Okay, so there are m columns and m columns and n rows. Okay, and the way this works is if J, okay, Mi or Jk is related, okay, it's equal to 1, sorry, they're equal to 1 if they're related. Okay, so this will be 1s and 0s and 0s and 1s, etc., and this matrix will describe this relation. To what extent are they related? What element is related to what? Okay. Turns out that this functor is not only a functor, it's an isomorphism. Okay, it's an isomorphism. All the information in this relation is going to be in, obviously it's an isomorphism of objects because this has only sets of numbers, finite numbers. This has sets of finite numbers. This is an infinite number of finite numbers, but like that, okay? But a relation in here is totally described by the matrix. The matrix, a Boolean matrix, totally describes that. So that's an isomorphism. But we can extend this, and it's very interesting to see it extended. Okay, so let's go through this. Okay. And we're here. And it goes as follows. So we have nat, whoops, didn't call it like that. Nat rel. Okay, let's go just remind ourselves what that is. Those are, the objects are natural sets of natural numbers and relations in between them. We also have nat par. Those are partial functions, and nat set. Okay. Let's go through what each one of these are. The objects here are sets of numbers, less than n, whatever, and the morphisms are relations. The objects here are sets of numbers and partial functions between those numbers. The objects here are sets of numbers and all functions between them. Okay, now if I erase the word nat here, I get set, which includes into par, which includes into rel, which we saw 5 minutes ago. Okay, now I already showed you that this fits in here, Boolean matrices, okay, and we call this F, and I told you that it's an isomorphism, and I told you, I showed it to you, it's an isomorphism. Well, we can extend this function with an F prime here and an F double prime here. Okay, I'm sorry, these are restrictions of the functions. Okay. Okay, so let's tell you what F prime is. F prime has the following property. Okay, take any partial function here and move it over to this matrix. It has the following property: has no more than one on each row. Could be column. I'm confused about how I wrote it in the book, but it doesn't matter. So a partial function is what? It's a relation, but each thing is related to each thing in one set is related to at most one thing in the second set. So that's what it means. No more than one in each row. Could have 0 ones in the row. Okay, as opposed to that, let's look at this. F prime. Okay. What's the difference between a partial function and a function? I told you set is not really, set should really be called fun. Okay. What's the difference between a partial function and a regular function? Well, for a regular function, every input has an output. This need not have an output. So has, not no more, has exactly. So no more means 1 or less. And this says is exactly 1 on each row. Okay, that's what a function is. By the way, in the book I also talk about isomorphisms. Okay, and that has exactly 1 on each column also. So every input has an output, every output has an input. Okay, so this is a nice example. These are nice functors, and they give you, this is not an isomorphism. This is an isomorphism. These are, not every Boolean matrix corresponds to a natural partial function. Not every Boolean matrix corresponds to a set function. Okay? Okay, great. I want to go back and talk about sets. I'm sorry, logic. Let's talk about logic. So there's something I drew in a previous matrix, in a previous video. Okay. And the idea is as follows. Let's go through this. The objects here are all propositions. The objects here are all propositions. Okay. And there's a nice functor like this called Q. Okay. Let's just remember what the morphisms here. There's at most one morphism here between one proposition and another proposition if one implies the other. Okay, and here there's a morphism from one to the proposition to the other proposition if there's a proof from one to the other. Now, there could be more than one proof from one proposition to another, so this doesn't necessarily have one morphism between any two objects. This has 0 or 1 morphisms between any two objects. Okay, this is bijective on objects. They both take propositions to propositions. Okay. Okay, and now we could talk about whether or not this functor is full or faithful. I'm sorry. It's barely ever faithful. No, it's not faithful because two proofs go to the same proof. The idea is as follows. If there's a proof, if there's a proof that A implies B, then definitely A implies B. Okay? This is not faithful, except under strange conditions, but not faithful, because there could be two proofs that go to the same thing. However, the question is if it's full or not. Okay, so let's think about what it means to be full. Full means for any two propositions here, it comes from a proof like that hits it. Okay, the thing is like this. Question. Does every proposition, if you know that A implies B, is there a proof for it? Okay? If it is, then this is full. If it's not, there could be things that are true. There's a proposition, A implies B, but there's no proof for it, and so then it's not full. Okay? We call full, the logicians call full complete. Okay? This logical system that corresponds to this is going to be complete. Every fact that A implies B there is a proof for it. Okay? Not full. If it's not full, then we call it incomplete. Incomplete is Gödel's incompleteness theorem. Okay? That means there's A implies B, but we don't have a proof of that. Okay, let's just remember Gödel's incompleteness theorem. What is that? Let me just remember the picture. Beforehand, you thought that true was equal to false. Okay, I'm sorry. True was equal to provable. Okay, and what Gödel showed was, no, there's true, and then there's provable. And his G statement is out there. The main point is as follows. If this is incomplete, so the image of this functor is all those things that are provable. If there's something outside of the image, that means there are propositions without maps and without that don't come from proofs. Okay, so out here. As opposed to that, if this was full, then you get this is complete, and you get something like this. Everything that's true is provable. Hold on, that's interesting. But we can also talk about something else. We could talk about two different types of systems. One logical system and another logical system, and you can think of this as a sub-logical system of that. Okay. Okay, and again, there's Q prime, and again, the proofs will be a subset of proofs. Okay. I'm sorry, didn't introduce this notation yet. This kind of means surjective on objects at least. Forgetful functor. Okay. Great. Now, two interesting things that happen a lot of times in logic. You ready? This can be complete. Okay, but then you look at the larger system. So this can be a complete system that's very well understood. Every proposition has a proof. Very nice. But there could be a larger system where this is incomplete. There might be more proofs, but this has more systems, so this would be incomplete. So that's one interesting thing that happens often. So this would be complete. And this would be incomplete. Okay, that's something that happens a lot. Okay, and then there's something else that also happens, namely, this would be incomplete. In other words, there are propositions where we don't have a proof, but if we add in certain axioms and we add in certain ways of doing things, this could be complete. Okay, so that's very nice. So again, lots of interesting logic can happen, and we all discuss it only with the notion of functors, inclusion functors. These are nice functors. Okay, you can stay up at night thinking about this. This is a very pretty picture. Okay, and drawing pictures. Okay, so you have Venn diagrams in here. Okay, you have Venn diagrams in here, and you want to see, this is, kept me up for a night. Okay, you have Venn diagrams in here, and you want to see how this and this subset relate to each other, and then you have this subset that goes definitely in this subset, but how they work. Okay, so some things like that. Anyways, nice stuff, nice things to think about. Nice things to visualize. Okay. Two more beautiful examples. Okay. I'm not going to go through all the technical details, but it's there, it's in the book. Okay, so let's remember what this is. This is the category of logical circuits, and remember the objects are natural numbers, okay? And they tell you how many inputs there are and how many outputs there are, okay? Okay, then we have Boolean functions. Okay, what are those? Those are functions where the inputs and outputs are zeros and ones, powers of zeros and ones. Okay, so they're functions, but not functions of numbers, or not functions of sets, not functions of anything. They're functions of bools, powers of zeros and ones. Okay, okay, and let's start with here. For every circuit, you have a Boolean function. So what's a logical circuit? There's circuits with inputs and outputs. The inputs are either on or off, zeros or ones, true or false, okay? And the outputs are zeros and ones, true or false. So if you give me a circuit, it's easy to come up with a Boolean function. This function says, when this is on, and this is off, and this is on, and this is off, and this is on, then the output should be off, on, off. That's exactly this. That's a Boolean function. But don't say off and on, don't say true or false, say zeros and ones. Okay, and so we have this. I call this functor, and I, describe it. I call it function description. Okay, so you take a circuit and you think of it as a function. Okay, great. These functions can be thought of as a Boolean matrix. We had that 3 minutes ago. Okay, kind of. Okay, you have a Boolean function, so let's go through this. The objects here are natural numbers, telling you how many Booleans you're accepting and how many Booleans you're outputting, okay? And the morphisms are functions between them, Okay, great. Okay, and here you have Boolean matrices. The objects are natural numbers. Hey, the objects here are natural numbers. The objects here are natural numbers. The objects here are natural numbers. Very nice. Okay, but the Boolean matrices tell you what, given a certain input, and the input could be 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, etc., what the output will be. Okay, and, okay, I'm sorry, this I call function evaluation. Okay, and this is a matrix description. Given a circuit, I can describe it with a matrix. I'm going to see this. Well, anyways, you can see the technical details like this. Okay, so that's a matrix description. Okay, I just want to say this functor in particular will be very, very important in quantum computing. Okay? In quantum computing, you have generalizations of logical circuits. You're going to have quantum circuits, and you can have Boolean matrices, but not really Boolean matrices. You're going to have other types of matrices, complex matrices. You can have unitary matrices, and this is going to be a generalization of that. Okay? So that's something we'll see way, way further on. Okay, great. That's what quantum computers are. They take quantum circuits and they build out matrices which describe it in some sense. Okay, when we talked about circuits, I said something, but I couldn't describe it because I didn't have enough of the toolbox to describe it. So we talked about circuits, and now we can talk about, and one of the things I said was, there are special types of circuits. Circuits are made out of ands and ors and nots and nands and nors and lots of different type of exclusive ors, etc., etc. But I said there's another category called NAND circuit. Okay, and these are circuits that only have one type of operation, NAND. Okay, for those of you who know computer operations, these are called Sheffer strokes, whatever. Okay, so let's go through it. The objects here are natural numbers, and the morphisms in between them correspond to all possible circuits. The objects here are natural numbers, and the morphisms in between them correspond to all circuits with only NAND gates. Okay, there's an inclusion of here into here. Okay, these are special types of circuits where you only have NAND gates. Now, great. Every time you have a circuit, you're really describing a Boolean function of what goes in and what goes out. Again, zeros and ones going in, zeros and ones going out. So every time you have a circuit, you're describing a Boolean function. How does that function, how does that circuit work? What does it do on real inputs? Okay, same thing here, you have that. Okay, namely, every time you have a NAND circuit is a special type of circuit, you have these Boolean functions that correspond to it. Okay, the amazing thing is there's a functor like that. Okay, I'm sorry, before we do that, this commutes, of course. Okay, and before we do that, we have a functor like this, such that, what does this say? You give me any circuit, there's a way of changing that circuit into a NAND circuit. Okay, and I told you beforehand, the reason why NAND circuits are important is because you want all your logical circuits to be one gate, okay, made out of one gate. It's a little bit easier to deal with like that. Okay, so you have your ANDs. So what happens here is your AND gates become special types of NAND gates. Your OR gates become special types of OR gates, etc., etc. That works. And by the way, what do you want from this circuit? So you have a circuit here, and you want a F of it. So let's see what you have a circuit here, and you want F of C here. What do you want of it? Well, you want it to do the same exact circuit that you want it to do the same function. You want it to perform the same thing that it does. So that's what that is. So you want this to commute. Let's just go through this. you can create the functor such that if you start with NAND gates and you think of it as a regular circuit, then F should not really do anything to it. It shouldn't change things, because what does F do? It takes out all your AND and ORs and NORs and changes them into NANDs. So if you start off with all NANDs, you should only get NANDs and no problem whatsoever. Okay. On the other hand, if you start with a circuit, if you start with a circuit and you get NAND gates, then you're not going to get the same thing as you had before. So this composed with this is not the original thing. Okay, they're going to do the same thing, but they're not the original circuit. So start off with a circuit, you're going to get a NAND gate equivalent circuit to that, and you're going to get that. Okay, great. So we saw a lot of examples. I'd like to spend a minute foreshadowing what we're going to do. Okay, so let's go through it. So this is section 4.1. Section 4.2 through section 4.7 is lots of different things about relating different categories. Okay, relating different categories. We're going to see natural transformations, which are things between functors. We're going to see special types of functors. We're going to see adjoint functors. We're going to revisit, now that we have the language of functors, we can redo and come back and redo all types of limits and co-limits and things like that. We're also going to see something called Monoidal lemma, which is again all about functors. So we're going to see lots of things about relating different functors and different relations between different categories. In section 4.8, we say, okay, we have the language of these functors, and we're going to have the ability to talk about logic. We're going to get a lot deeper into logic and what we mean by that, and we're going to use that all as functors between logical categories. And so things are going to be, that's a mini course that's going to dive into what logic means for a category theorist. Okay, let's just talk about chapter 5. So chapter 4 is about relationships between two categories. So we finished our introduction to category theory, and now we start monoidal categories. So chapter 5 is the beginning of monoidal categories. And what we're going to see is a lot of these categories have extra structure, okay, called monoidal categorical structure. And that's very good. A lot of these categories have extra structure, okay? Great. And so we're going to see a lot of those examples in chapter 5. And then chapter 6 is called relationships between monoidal categories. And what we're going to see is as follows. In this section, we talked about a functor from A to B. Okay, so you have a category here and a category here. In chapter 5, we're going to say, you know what, this category has extra structure. There's some other operations that we can do on this category. And you know what, this category has some operations that we can do in this category, et cetera, et cetera. We're going to see this in chapter 5. Okay, and what we're going to do about in chapter 6 is we're going to see, you know what, not only is this functor here, but this functor respects these extra operations. Respects that extra structure, and that's going to be really cool. So what we're going to see is that when we get to chapter 6, we're going to see a lot of these functors once again, and we're going to show how not only is there a relationship between this category and this category, but this category has extra structure, this category has extra structure, and the functors that relate them respect that extra structure, which is again a unification thing. It means that what's done here, the operations that are done here, are also done here, and they have the same type of structure. So we're in for a beautiful journey. Okay. Again, any comments, criticisms, or ideas of how to make these videos better, please let me know. Take care.